Now Anahit will be with us, and this will be the last presentation of today, and then it will be a raffle here. If you go out, don't forget to come back for the raffle, but I strongly recommend that no go out and listen to Anahit. It will be great.
Quit, and then I start presenting. Yes, excellent. Do I start when? Right away? Okay, that was fast. So imagine you have built this simple serverless architecture in the cloud. You have picked the services you want to use, you connect them together, and everything just works like magic. So much so that you decide to go all the way to production with it. And all of a sudden, hell breaks loose and everything starts to fail in all possible ways, shapes, and forms. And there's nothing you have done wrong, you think, well, maybe except for not reading all the extensive documentation and all the libraries, about all the libraries and components that you are using, but who does that nowadays anyway, right? So what's the next logical step? Maybe you swear off using the services or architecture in question altogether because, well, it just doesn't work. And what's wrong with the cloud anyway? Why doesn't it work? And serverless is just an expensive fad. Let's just all go back on-prem and use good old monoliths. Though, purely statistically speaking, we probably should assume that the problem is not necessarily the cloud or the cloud provider, maybe not even the service or the architecture in use. So what is it then? Murphy's Law says that anything that can go wrong will go wrong. Though I personally prefer the more extended version of it that says anything that can go wrong will go wrong at the worst possible time. My name is Anahit. I'm a lead cloud software engineer at the European company called Solita, and I'm personally based in Finland. And I'm also an AWS data hero. And I always need to do this disclaimer, AWS doesn't tell me what to say, they don't pay me. I only share my personal thoughts and experiences here. And there's a funny thing I noticed after becoming a hero. People started to come to me with this smirk on their face and saying, so tell us now, why doesn't the cloud work? What's wrong with it? So I'm here today to answer that. Well, maybe not exactly that, but I want us to look together at something that we as humans usually don't feel comfortable. Failures. And to that I say, if something doesn't feel comfortable, let's do it more often. And I hope this talk will help you to become a bit more curious and aware of patterns that others don't necessarily see. And maybe gain some tools to ask questions and make conscious and critical decisions, take control into our own hands rather than believing in magic, and also become a little bit paranoid, but in a good way. And to borrow words of Martin Klebman, in distributed systems, suspicion, pessimism, and paranoia pay off. But before we start talking about the distributed systems and all the failures, let's get back to our story for just a little bit. It actually had a prequel to it. So, once upon a time, you were just a developer who started developing software that was supposed to run on a single machine somewhere in a data center. And all you needed to worry about was the so-called functional requirements. So your code does what it's supposed to, and it has as little bugs as humanly possible. Those were your definitions of reliability. And of course, there could have been some occasional failures with the hardware, but you didn't care about them that much. Things were mostly quite predictable and nicely deterministic. Things either worked or they didn't. Next thing you know, you find yourself in the cloud, probably using the abstraction of the virtual machines, and all of a sudden you start develop software that requires you to think about the non-functional requirements. Things like certain levels of availability and scalability. Also, reliability and resilience get a whole new meaning, and you still need to think about those functional requirements that you had. But the complexity level just got up, and you need to worry about so much more. And failures are kind of slowly starting to be more prominent and a bit less deterministic. Welcome to the dark side, the wonderful world of distributed systems, where with great power comes great responsibility. But things didn't stop there, and next thing is that we are jumping over to the serverless and fully managed world, and things start to be simple again. The cloud providers take care of these major utilities for us, so things like reliability, availability, scalability. You don't see any machines around. Moreover, the word serverless suggests that you don't need to be looking for any machines around. And things are just simple and easy. You just focus on your functional requirements, you pick the pieces, you connect them together, and everything works like magic. The end. Though we kind of know that's not exactly how the things go. Because anything that can go wrong will eventually go wrong. So what can go wrong exactly? Let's look at distributed system, the cloud, the serverless in really simplified terms now. So distributed system, just a bunch of machines connected by a network. And while it provides you a lot of new and exciting ways to build solutions and solve problems, it also provides you a lot of new and exciting ways for things to go wrong. Because resources you are using are not limited to a single machine anymore. They are distributed across multiple machines, multiple server racks, data centers, maybe even geolocations. And instead of just one machine that can fail, well, now we have plenty. And those failures can happen on any level. It can be software or hardware failures, operating systems, hard drive, CPU, you name it, all the possible options. And all of those failures can happen completely independently of each other in a pretty non-deterministic way. And the worst thing is that all of that machines talk to each other over a network. And it is notorious for one thing: whenever communication happens over a network, it will eventually fail. And the cloud, any cloud, basically is built on top of such distributed systems. That's where its superpowers come from. And the cloud provider takes care of the most difficult part of managing the underlying infrastructure for you, abstracting it away from you, abstracting the lower level of complexity away from you, and also giving you access to the shared pool of resources such as compute, storage, network, and doing that at a really massive scale that no individual user could ever achieve. But especially at the big scale, if something has a tiny little chance of happening, it most certainly will. And serverless and managed services are a step up in the abstraction ladder. They make the underlying infrastructure almost invisible, almost magical. So much so you might even forget that it's there. But by using serverless and managed services, we didn't just magically teleport to a different reality. We are still living in the very same messy physical world, and we are still using the very same underlying infrastructure with all its built-in complexity. And a higher level of abstraction, of course, makes a lot of things much easier, just like a higher level programming language would do. But it also comes with a danger. Being seemingly easy to use, it can give you this false sense of security. And that makes spotting the potential failures that much harder because, well, they are also abstracted away from you. And the reality is failures didn't go anywhere. They are still there, embedded in the distributed system. And as Leslie Lampert said already in 1987, a distributed system is one in which a failure of a computer you didn't even know exists can render your own computer unusable. We can kind of rephrase this for serverless as well, but with serverless, we don't see failures as hardware failures or blue screens. Failures usually manifest in a different, sometimes less obvious ways. Now let's climb one last step in that abstraction ladder and talk about distributed applications or building distributed applications on top of serverless and managed services. So in essence, we split the problem at hand in smaller pieces, and for each piece we want to pick a service or a resource we want to use. We connect all of them together with messages, events, HTTP requests, all of the things using a network. And in essence, a distributed application is mirroring the underlying distributed system. It also provides all these exciting new ways of building architectures and solving problems, but again, with great power will come great responsibility, and the architecture that you are trying to build will probably be susceptible to very similar trade-offs as distributed systems. They probably will have a higher level of complexity. Every component will potentially fail at any given moment in the most non-deterministic way possible. And whenever there is any communication happening over network, well, it will eventually fail. And the special case of these distributed architectures are so-called data applications. So applications where we deal with collecting, storing, processing large amounts of data, which can be anything that you want to collect, process, and store. And these large amounts of data, large volumes, make it somewhat easier to spot the potential failures because, well, if something has a chance of happening at big scale, it most definitely will. But with data applications, it's usually a bit more challenging to spot those failures as well because they are not as obvious as with, let's say, client-facing applications, where you just see an error right away. And moreover, when errors are happening while processing the incoming data, nobody is going to resend you that data. Once it's gone, it's gone. So how do we deal with all that failures? How do we make our distributed architectures more resilient? And while we are mirroring the underlying distributed systems, we should look at how the cloud providers are dealing with the failures in distributed systems, because they do have quite some experience with that. And of course, there's a lot of complex mechanisms and algorithms at play, but the two of the most essential tools for building more resilient distributed systems are also seemingly simple. They are timeouts and retries. And those are the things that we absolutely need to be aware of when we are building distributed architectures. I call them these superpowers. And unlike superpowers, they are real, but they are very powerful and can be used both for good and evil. And we will soon see what I mean. So you might have noticed, but by now I didn't even mention any cloud providers, any specific services whatsoever, because all of those things are inherent to all of them. They all suffer from them. But now, finally, it's time to move on from our fictional story and maybe confess that it wasn't as fictional after all. And in fact, this is something that happened to me, at least to some extent. So I was working with this customer where we're building this simple yet powerful distributed architecture for near real-time data streaming in a pretty big scale. And we had a producer that got data that we wanted to collect and process, and for that, we connected it to Amazon Kinesis data streams. And on the other end, we connected AWS Lambda to it to consume that data. And just like that, we built a data processing pipeline. And everything was just fine until one day we realized that we were actually losing data, and we had no idea it was happening. Thank you, higher level of abstraction. So what exactly was going on there? First, what is Kinesis Data Streams? If you are not familiar, it is a fully managed and massively scalable service to stream data. After you write the data to the stream, you can consume it or read it for the next 24 hours, or you can configure it to stay in the stream for up to a year. And during that time, you can process and reprocess that data as many times as you want, but you cannot delete the data from the stream. Once it gets to the stream, it stays there for at least 24 hours. And Kinesis is a very powerful tool. It doesn't require you to use or to configure any servers or clusters, and it comes with a pretty impressive scalability. And to achieve that scalability, Kinesis uses the concept of a shard, which is basically an ordered queue within the stream, and each stream will be composed of multiple such queues. And each queue or each shard will come with capacity limitations. You can write 1 megabyte or 1,000 records of data per second to each shard. But you can have as many shards as you want in your stream. So the number of shards is theoretically not limited. So you can have as many shards as you want to stream as much data as you need. And to stream that data or to get it to Kinesis, there are basically 2 API calls that you can use. You can either write individual records, or you can batch up to 500 records and send them in a single put records API request. And batching in general is a more efficient and less resource-consuming way of doing API calls, especially if we think about data-intensive applications, where if we would send individual queries or requests for every single record, that would be very resource-consuming. But being so powerful, of course, it comes with some extra responsibilities, and we will get to that in just a moment. So we have established by now that failures in distributed systems and distributed applications are pretty much inevitable, especially at a bigger scale. So how do those failures manifest at this higher level of abstraction of a service like Kinesis? Well, it's actually pretty straightforward. Your API request to Kinesis can either fail or time out sometimes. And there's a good and bad news. So the good news is that if you are using AWS SDK to make those requests, those API calls, AWS SDK will take care of the most of the problems for you. Because after all, AWS knows firsthand that failures will happen. So they have built into the SDK one of those essential tools for building better, more resilient systems, or a superpower, as we call them, the retries. That was the good news. The bad news is that now with the retries, we can potentially turn something that is a small intermittent problem into a massive one. Because retries can have unexpected side effects and unexpected blast radius. And they can cause this ripple effect of cascading failures down your system and ultimately bring the entire system down. So we need to be extremely careful of how we use this superpower. Luckily, AWS SDK comes with built-in safety measures. So SDK will only take care of the failures or the failed requests that failed because of so-called transient errors. So things like service unavailable or any other 500 errors or timeouts, so retriable errors. And it will retry those retriable errors on your behalf behind the scenes, but it will stop after 3 retry attempts. It will not continue. And also between the retry attempts, it will use the so-called exponential backoff, which basically means that the time between consequent retry attempts will be increasing exponentially. And those might seem like really small details, but those are actually crucial things that can either make it or break it. Because we only want to retry when it actually can help, so with transient errors. We also want to limit retries and stop retrying when it doesn't help anything anymore, it doesn't improve the situation, to avoid this ripple effect of cascading failures down the stream. And we want to spread those retry attempts as uniformly as possible to avoid overwhelming the underlying system, but this simultaneous burst of retries that we could send to it. So we want to protect that underlying systems by configuring smarter retries. And SDK gives you this superpower and allows you to configure some of those retry settings. In the same way, it gives you another superpower. It allows you to configure timeout-related values. And if you think now timeouts are not a big deal, well, think again. Because in distributed systems, timeouts are pretty much a given. Let's take a look under the hood once again in really simple terms. So when we are interacting with the serverless or any other service for that matter from our code, we are basically using API calls that are abstracted away from us as SDK method calls. And those look exactly the same as local method invocations. But let's not let that fool us, because we do know that the network is still there. It is just abstracted away from us. And every request sent over a network, like an API call to Kinesis, can eventually fail. Moreover, it's almost impossible to say if the request actually went through or not, because the failure can happen on so many different levels. The request might fail, maybe the request is waiting for the server that is busy, so the timeout comes up, or maybe the processing actually failed, who knows? Or then the processing succeeded, but you never got the response back. There are many different options that can happen, but the end result is still the same. We might end up waiting for something that might never happen. And this can happen to any service, no matter how serverless or not it is. This can happen to Kinesis as well. So to avoid that waiting forever, SDK or AWS has built into SDK this other superpower, the timeouts. And it gives us that superpower by allowing us to configure it. But of course, it can be used both for good and evil, just like retries, because configuring the correct timeout values is not as simple as it seems. And it will come, as any other architecture decision, it will come with trade-offs. If you have a too long timeout, well, it will be ineffective and probably cause some latencies in your application. Too short timeouts might mean that you will start retrying too early and you will not give enough chance for the original request to go through. So that way you will overwhelm the underlying system even more and cause those ripples of cascading failures. So it's very important to configure appropriate timeout values. But on top of all that, the appropriate timeout value will actually be different for every single service that you're going to use. But for all the services, AWS SDK will wait for 2 entire minutes before it decides to time out your request. Just think about it for a second. We are dealing with low latency systems like Kinesis, DynamoDB, anything else. And here we are sitting for 2 minutes waiting to time out the request before we retry. And add to that all the possible retries on top of that, and we might end up just sitting there waiting for nothing. So, as I said, extremely important to configure appropriate timeout values. And this brings us to the first reason of losing data in our sad story with the serverless architecture. So, just blindly going with the defaults and waiting for too long can exhaust the resources of your producer, and consequently, it will not be able to take up new requests, and it will lose data. And that's exactly what we were observing. And because of likely a temporary small intermittent error, something like network glitch or maybe some issues with the service, we now turn that temporary error in a complete system outage, which is basically the opposite from what we want a resilient system to be. So make sure you use those superpowers wisely and don't just blindly go with the defaults, because defaults can be really dangerous. I'm sorry. Okay, so far I have been talking about the errors, failures that are innate to distributed systems in general. But there's also different kind of failures. And those are caused by the cloud providers themselves on purpose. And those are the failures that are related to service limits or throttling. And it can be especially confusing because, especially with serverless, we are promised scalability. And somehow we have this tendency to assume infinite scalability. But if something is too good to be true, it's probably just that, because nothing is infinite, nothing scales infinitely, and service limits are a manifestation of just that. And sooner or later, we better face the reality. And the reality is, we don't have the entire cloud at our own disposal. We are sharing the underlying resources with everybody else. And this, of course, is a good and bad thing. It gives us this huge pool of resources that we can actually share and use. But this also means that there can be a user that can try to monopolize those resources. And while the resources are not infinite, this will mean that it will degrade the service for all the other users. So service limits are there to ensure that that doesn't happen, and throttling is a way of ensuring those service limits. And for example, in case of Kinesis, we had this 1 megabyte or 1,000 of records of incoming data per second, and once we reach that limit, all the other requests will be throttled, so they will fail. And this brings me to the next reason for losing data in the story. So I said that AWS SDK will handle most of the failures for you, right? There is a catch. Because in case of batch operations, like we have put records here, instead of only handling the failures of the entire request, we should also handle so-called partial failures. Because you see, batch operations here, they are not atomic. They are not either all succeeds or all fails. Part of your batch might go through, while the other part will fail, and you will still get a success response back. I will go one step further and say that every single record in your batch can fail, and you will still get a success response back. So it's your responsibility to detect those failures and to handle them. And the main reason for this kind of failures are exactly throttling and exceeding service limits or reaching the service limits. So when implementing retries for this kind of partial failures, or any failures for that matter, we have seen already that there are 3 key elements that we need to keep in mind, just like AWS SDK does. So we only want to retry if it will help the situation, so transient failures. We want to set the upper limit for the retries. We do not want to be retrying forever. We want to stop if it doesn't improve the situation. And we want to use the exponential backoff or a proper backoff between retry attempts so that we will spread them uniformly and we do not overwhelm the underlying system even further, because we probably are already dealing with throttling. So we are already pushing the service to its limit. So we don't want to push it over the edge. We want to kind of improve the situation, not escalate it with the retries. And for that, exponential backoff and jitter is an extremely powerful tool. And jitter is just a random component that you add to the exponential backoff. And that's actually exactly what SDK uses. I just didn't mention it on the previous slide. And this extremely simple tool is also extremely powerful. It can save you a lot of gray hair and improve the retry attempts pretty dramatically. So if you remember anything at all from this talk, let it be partial failures of batch operations and retries with exponential backoff and jitter. Those will help you while you're building any sort of distributed applications. And to borrow words of Gregor Hoppe, retries have brought more distributed systems down than all the other causes together. And this doesn't mean that we shouldn't retry. We just need to be very mindful about how we do it. We don't want to kill the system that we are trying to fix. Speaking of which, let's also see what happens when we let the error handling slide on the other end of things. So we just blindly go with the default. So what happens then? It is pretty easy to go with the defaults, right? You don't need to worry about it, but real life is rarely easy. And turns out things can escalate pretty quickly. So remember our architecture, we had this Lambda function reading from our Kinesis stream. And Lambda itself is a perfect representative of the distributed architectures. It is composed of multiple different components that are working together behind the scenes to make it so very powerful. And one such essential component is called the event source mapping. It is hidden underneath the Lambda abstraction, but when you are attaching a Lambda function to read from Kinesis stream and some other event sources, you are in fact attaching an event source mapping to that resource and then pointing your Lambda function to the event source mapping. And it will be the event source mapping that will pick the records, that it will batch them together and send them to your Lambda function. And those batches will be picked from all the shards in the stream in parallel, and you can configure to have up to 10 lambdas reading from each shard in the stream. And this is called parallelization factor. And in that way, you will essentially have up to 10 times as many concurrent lambdas reading from your stream as you have shards in your stream at all times. And this is where the power of distributed computing kicks in, because you can parallelize this process of consuming the stream. You can add more power to it. But with great power, well, we know how that one goes. Here, it's pretty easy to hit another important service limit. So Lambda is awesome. It scales, but it also comes with limits. And this one is Lambda concurrency limit. So this basically means that you can have a limited number of concurrent Lambda invocations in the same account in the same region. And by default, it's 1,000, though I've heard that new accounts only get 100, which is like very low. It is a soft limit. You can ask for an increase, but there still is going to be a limit. And once you reach that limit, all the new Lambda invocations will be throttled. They will fail. So imagine you have a stream with 100 shards. You configure the parallelization factor to 10. And here you are having 1,000 lambdas just reading from your stream at all times. And things are going to be great until someone else somewhere in your account, in your region, deploys a very business-critical lambda, and that lambda starts to fail. Because your stream consumer consumed the entire lambda concurrency limit. So this is a limit that can have a huge blast radius and can potentially cause this ripple effect that can go way beyond your own architecture. So you need to be extremely careful. But now let's get back to reading the records from the stream. So what happens if that fails? Once again, there is a good news and the bad news. So the good news is that the wonderful event source mapping comes with extensive error handling capabilities. But to use them, you need to know where to look. So the bad news is that you are very likely to just blindly go with the defaults. And we know how that one ends. So what happens by default if Lambda fails to process a batch of records? Let's say there was some corrupt data, some record couldn't be processed, you didn't implement proper error handling, Lambda throws an error. What happens next? by default, Lambda will try to process the failed batch of records over and over and over and over again until it either succeeds, which we know it won't, there is a corrupt data, or the data in the batch expires, which in case of Kinesis, it's at least 24 hours. So for at least 24 hours, Lambda will be processing that failed batch of records over and over again without any success, just consuming resources and doing a lot of damage, potentially. And while doing all that reprocessing or retrying, Lambda will likely reprocess some of your data. Because you see, from perspective of the event source mapping, either entire batch succeeds or entire batch fails. So even if you already managed to process some of the records in the batch successfully, like 1 to 3 here, the entire batch will fail, and the entire batch will be retried over and over and over again. So you will have a lot of record reprocessing. And bad things don't stop there neither, because while Lambda is busy with all that reprocessing, no other records are being consumed from that stream, or from that shard, I'm sorry. The shard is stuck. All the other shards go on with their lives, but that one shard is stuck because of just one bad record. And that's why it's often referred to as a poison pill record. And this is also a logical way of working. It's not some black magic or some evil trick, because Kinesis promises you a shard-level ordering. So the records will be in the shard in the same order that you wrote them in. Which means that if Lambda just decides to jump over some of the records and then maybe return them back sometime later, the ordering won't be guaranteed anymore. But that doesn't make the situation that much better, right? So after all that reprocessing, the data finally expires and finally leaves the stream. The batch is partially in process, but that's life. What happens next? At least Lambda can now start picking up new records and continue processing the data. But at that point of time, your shard is probably filled with records that were written around the same time as the already expired one. And this means that they expire around the same time. So you might end up in a situation where your Lambda will not have a chance to process those records, and they will keep expiring and keep being deleted from the stream. So you will end up with this overflowing sink where you can't drain the water fast enough, and it will just overflow. So though we started with just one bad record, we might potentially end up losing a lot of valid and valuable data. And you guessed it, that's exactly what we were seeing in our story. Just like with poorly configured timeouts and retries, we turned a really small intermittent error, a one bad record, not a big deal, we turned it into a complete system outage. And we were losing data, we were causing delays, we were causing duplicates, we were using unnecessary resources, we were generating costs, and all of that ultimately leading absolutely nowhere. And all of this because we didn't know better and just blindly went with the good old defaults when it comes to error handling. And I just need to bring the wise words of Gregor once again. And luckily, there are many relatively simple ways to be smarter about retries with Lambda. And first and foremost, we need to configure those error handling capabilities that event source mapping gives to us. And we know that some of the most important things are timeouts and retry limits. So event source mapping gives us a capability of configuring those, but by default, both of them are set to -1, which is infinite. So we need to be extremely careful with that. And event source mapping comes with other very useful error handling capabilities. I'm not going to go into details, but you need to know about them in order to use them to full potential, and they can be extremely useful. And you can use them in any combination that you want, but whatever you do not go with the defaults. So we have seen today firsthand that sometimes we can cause more problems while trying to fix them. And this is especially true if we don't make these conscious and critical decisions and just make the matter slide when it comes to error handling. And those decisions will come with trade-offs, things like retries and timeouts. When configured properly, they can be extremely useful. But if we just let them slide, well, they can backfire. And they can turn our small intermittent problems into huge ones. And instead of making our architecture more resilient, they will actually achieve the exact opposite. So next time you build a distributed architecture, I encourage you to be brave, to face the messy reality of the real world, to take control in your own hands rather than believing in magic, because things are not magical, and that's a good thing. And distributed systems and architectures are very powerful, but they are hard. And that doesn't make them inherently neither good or bad. And cloud, and especially serverless and fully managed services, they take away a lot of that complexity. They abstract it away from us. But complexity didn't go anywhere. It's still there, which, again, doesn't make them neither good or bad. And while we don't need to know every single detail about every single service, this is borderline impossible, there are fundamental things that are inherent to all the distributed systems and cloud in general, so things like timeouts, partial failures, retries, backups. And we absolutely need to understand those fundamental things, because without that, we are just moving in the dark with our eyes closed and just hoping for the best. And finally, though distributed systems are hard, they can also teach us a very valuable skill: to embrace the chaos of the real world. Because every failure is an opportunity to make our architecture better, to make it even more resilient. And though it's impossible, no matter how hard we try, it's impossible to build something that never fails. But there's one thing that we can do. We can learn and we can grow from each failure. And as Dr. Werner Vogels likes to remind us, everything fails all the time. That's just the reality of things. So either in life in general or with AWS services in particular, I'd argue that the best thing that we can do is just to stay calm and be prepared when those failures happen. And that's it from me for today. Thank you all very much. I will take the question off the stage because I'm over time. Thank you.
Thank you, Anahit. And here's your presentation.
Thank you. Thank you so much. And I'm sorry for the too long talk.